So my name is Scott Denning. I'm a professor of atmospheric science at Colorado State University. And I met Ethan on this amazing adventure on semester at sea that we just got back from. And I would like to talk with you today about climate change. I know you've probably already heard about climate change, and I know that you probably already kind of know how you feel about it. And I will ask you to be a little bit open-minded, because I got three different things I want to talk about with regard to climate change today. They all start with the letter S, so it's pretty easy to remember them. The three S's of climate change are simple, serious, and solvable. And when I talk about the three S's, I always cover all three. Probably most of the stuff you've heard about climate change before has been the middle S, which is like, oh my gosh, it's very serious, it's scary. And that is true. It is actually very serious and very scary. But that is not enough to understand the seriousness. It's actually really important to understand the mechanism. That's the simple. So simple is how does it work? Serious is why is it bad? And solvable is what are we going to do about it? And it's particularly important that we don't just stop with that middle S, that we go on to that third S, which is the solutions, because otherwise, you know, you might as well just throw up your hands and say, "Oh, forget it. This is just the end of the world. So I'm checking out." So it is a little odd that I will start with simple, because I am a professor of this stuff, and I have spent the last 30 years of my life sort of working on this. And if it's so simple, how come I still have a job? So there you go. Anyway, the point here is that the basic mechanism of how climate change works is very, very simple. And it's important that you understand that, because you won't understand how serious it is unless you understand the mechanism. So ever wonder why it's warmer in the day than it is at night? Did you ever wonder why summer is warmer than winter, or Phoenix is warmer than Fargo? Probably not. You probably already know these three things. But if you stop and think about it for a minute, you will realize that the answer to all these questions is the same answer. The reason why day is warmer than night is the same as the reason why summer is warmer than winter is the same as the reason why Phoenix is warmer than Fargo. And the reason is because heat in minus heat out equals change of heat, right? This is a fundamental property of the universe. When you put more heat into something than you take out, it warms up. When you take more heat out than you put in, it cools off. Now, around, the weather, everybody's experience of the weather, that's mostly about heat coming in and out the sides. That is, like, on one day, it might be cold and rainy. On the next day, it might be warm and sunny. But that's not because the overall heat of the Earth has changed. That's just that the air that was here yesterday blew away, and it was replaced by air from a different place. But when we look at the Earth as a whole, the climate of the planet, there are no sides. This is absolutely fundamental. The Earth is round, and no matter how much sideways movement of heat you have due to the weather, it doesn't change the total amount of heat. The only way that the total amount of heat for the whole Earth can change is through the top. And you're not used to thinking of the Earth as having a top, but it does. The top of the atmosphere, the incoming heat, pretty darn obvious. It's the sun. The sun beats down on the Earth, and that puts heat in, heat in, heat in. But if that was the whole story, remember, heat in minus heat out equals change of heat, the Earth would just get hotter and hotter and hotter until it melted and boiled and vaporized. End of the world, right? So that can't be the whole story. There has to be heat getting out all the time, and there is. It's just that you can't see the outgoing heat, okay? The incoming heat, we can see, it's sunlight. The outgoing heat is invisible, literally invisible. It's infrared radiation. Now, you can't see it, but that doesn't mean it's not there. If you've ever turned on an electric burner on a stove, you can feel the heat coming off of that sucker before it ever turns red and start to see it. And that's infrared radiation. And the Earth is constantly sending infrared radiation out to space. And if the amount of heat in minus heat out, if they get out of balance, even a tiny bit, then the Earth will warm up or cool off to compensate. So that's exactly what the greenhouse effect is all about. Imagine a house, and down in the living room, you've got a wood stove, let's say, And then up in the attic, you got no insulation and it's cold outside. So you crank in the wood stove and it gets nice and toasty in the living room. But the heat is going out through the attic all the time, right? So the temperature in the living room will adjust until the heat coming out of the stove is equal to the rate the heat is going up through the attic. But then if you go in and insulate the crap out of the attic, even if the wood stove stays at the same level, the living room is going to warm up, right? You haven't actually added any heat to the system. You've just slowed down the heat loss. And since the heat in is the same, but the heat out is less, the change of heat is positive. You actually warm up the living room because of the insulation. And this is exactly what putting CO2 in the atmosphere does to the Earth system. Now, there's this one little part I got to explain, which is a little weird. It's a little physicsy. It's a little chemistry-y. It's a little bit more than, you know, your average high school science class, but it's not that hard to understand. Okay, so nearly all of the molecules in the atmosphere are just these two kinds. The one kind is oxygen at the top, O2. And the other kind is nitrogen at the bottom, that's N2. And O2 and N2 constitute like 99% of the air. And as those outgoing infrared rays are going out through the atmosphere, they can interact with these molecules, but not very well. And the reason is, okay, so this is the part that's maybe a little hard to understand if you haven't had some kind of physics, but molecules are made of atoms. Atoms are made of protons, neutrons, and electrons. In the center of each atom is a nucleus, which is positively charged, and there's electrons that go round and around. And in a chemical bond, which is indicated by these dark lines, some of the electrons are shared. So there's this like cloud of negatively charged electrons in between the two atoms of the molecule, and along comes this IR photon, right? Infrared rays coming out to cool the Earth, and it can interact with that cloud of electrons and get them kind of like sloshing back and forth in the magnetic field. You can think of it like woo, 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 woo. It doesn't really make that sound. I just make that part up. But the woo, 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 woo thing is the conversion of electromagnetic energy into vibrational energy of the bond. But because 99% of the molecules in the atmosphere are diatomic, that is, two atoms of the same element, they are perfectly symmetrical. They're identical on either end. And this is the only way you can rearrange the geometry of a diatomic molecule. There are a tiny number of molecules in the Earth's atmosphere that are not diatomic, that actually have three atoms instead of two. And the most abundant atoms or molecules of that kind in Earth's atmosphere are these two. The top one is called carbon dioxide, and the bottom one is called water. And CO2 and water both have three atoms instead of two atoms, and therefore they have more ways that they can interact with the infrared radiation than the rest of the air, the O2 and N2. So I only got the two hands, so let's let this be carbon. It's my head, oxygen, oxygen. Now I'm a CO2 molecule. Along comes that infrared photon. You go woo, and you know now it's like absorb this energy from the surface. But then the molecule can de-excite, whoa, back to its ground state. Out will come a photon of infrared energy, just like O2 and N2. But there's more, because unlike O2 and N2, the CO2 molecule can go each one of these different ways of rearranging the shape of the molecule will absorb a different wavelength of infrared energy, a different energy level of IR photon. And that's what makes CO2 a greenhouse gas. It's not because of greed or capitalism or Al Gore. It's just bad luck that the gas that's produced when we set carbon on fire has three atoms instead of two atoms. And so there are more ways it can wiggle than the O2 and N2 molecules that constitute 99% of the atmosphere. Now, the water vapor molecule is even more interactive with the photons because it's bent. So it's got like this thing that it does, and this thing, and all these different ways of wiggling. But the thing about water vapor is, if you put loads and loads of extra water vapor in the atmosphere, it rains. And so the water vapor is then removed from the atmosphere. The atmosphere can't hold very much water vapor because if you put extra in there, it just falls back out. But that doesn't happen for CO2. The CO2 is basically permanent. The extra CO2 just stays in the atmosphere and accumulates over time. So this is why when we worry about climate change, we're mostly worried about the CO2. The water vapor kind of takes care of itself. It adjusts to the temperature, whereas the temperature adjusts to the CO2. So this is the greenhouse effect. You've seen the cartoon before. The sun beats on the earth. Some of it reflects off, but the part that doesn't reflect off gets absorbed. That is heat in. That is the warming of the earth. And it tries to get rid of all that heat by infrared radiation. That's these red arrows here. Most of it gets recycled, actually gets absorbed by those CO2 molecules in the sky, re-radiated down. A little teeny bit of it gets out, but most of it is actually re-radiated back down by the atmosphere, and that's what keeps us warm. If it weren't for this, super duper bing bong effect of the CO2, the Earth's climate would be uninhabitably cold. The Earth would be a like frozen ball of ice, forever orbiting dead in the solar system. Thank God for the greenhouse effect that keeps us warm. Okay, so believe it or not, all of this was discovered almost 160 years ago by a scientist named Eunice Foote. In the 1850s, she put jars with different gases in her garden, and she measured the changes of temperature of the air with different mixtures of gases, and she came up with this idea that it was actually the CO2 in air that was responsible for the unusually warm climate that the Earth has. So it was later explored in more detail in the 1860s, about the time of the U.S. Civil War, and it really comes down to common sense. Every time you double the number of these beep boop molecules in the sky, it adds 4 watts. Now, you guys are probably too young to remember these things, but these were 4-watt light bulbs that we used to use as night light bulbs when my kids were little. 4 watts on every square meter. So if you just look down where you are and look at something that's about a square meter, like, I don't know, carpet tiles or desks or something like that, that's sitting around you about a square meter, if you double the amount of CO2 in the atmosphere, it adds 4 watts to every square meter of the Earth forever. So it's like putting a little light bulb there, but the whole planet covered with these little light bulbs. If you did that and you left them on forever, the world would be a little bit warmer, right? Not necessarily a lot, because they're just little night light bulbs, but there's boatloads of them. They're everywhere. There's every 3 feet, a little 4-watt night light bulb. Believe it or not, all of this was known before light bulbs were invented. I told you Eunice Foote first figured it out. This guy, John Tyndall, did a bunch of measurements during the U.S. Civil War and was able to show quantitatively that the CO2 was warming the climate. So leads me to what I call common myth number 1 about climate change, is that scientists expect a warmer future because it's been warming up recently, and it has been warming up. No doubt the temperatures used to be cooler, and then they started to rise, and then they started to rise much faster around 1980. But that's not how we figured this out. We knew this was coming 100 years before 1980. In fact, the reason that we expect a warmer future is that we know that when we add heat to things, they warm up, right? So if you put a pot of water on the stove and you put a bunch of heat in the bottom of that pot of water, you're putting heat in faster than it can get out, and the temperature of the water will go up. This is not rocket science. This is not hard to understand. We know for sure that the CO2 in the atmosphere traps the outgoing heat, and we know how much CO2 traps how much heat, and we've done that like for 150 years in the lab, and we've done it outdoors, and we've done it from airplanes, and we've done it from balloons, and we've done it from satellites, and we're just absolutely sure of the relationship between the heat absorbed and the CO2 of the air. So we are really not just doing some kind of correlation here. We understand the mechanism very, very well. So that brings me to the serious part. Because climate change is very serious, and we have to deal with it, and we have to deal with it whether you like it or not. So let's talk about how much warmer is it going to get? Well, it depends. First of all, these are maps of estimated warming in the future under a high emissions scenario at the bottom, a medium emissions scenario in the middle, and a low emissions scenario at the top. And the colors show how much warmer it's going to get. So obviously, the more CO2 we emit, the hotter it gets. But that's not all that it depends on. It depends on whether you look at the land or the oceans. The land warms up way more than the oceans do. And that's because the oceans, when you put all that extra heat into the oceans, most of that heat gets used to evaporate water instead of change the temperature. So the oceans don't warm up very much, but the land warms up a whole lot more. In the northern hemisphere, it warms up a lot more than it does in the southern hemisphere. And that's because the northern hemisphere is mostly land and the southern hemisphere is mostly oceans. And thirdly, if you notice that way up in the Arctic where it's icy and snowy, it warms up more than anywhere else on Earth, and that's because the snow and ice reflect a lot of sun to space, and if you warm it up enough to melt the snow and ice, then you get extra heat, not just the 4 watts from the doubling of the CO2, you also get the extra absorbed sunshine. So here in the middle of North America where I live, this is about 3 Celsius of warming with a low emission scenario, and it's about 6 Celsius of warming with a high emission scenario. I know you guys don't live in the middle of North America. You live on the coast or near the coast, so you won't warm up as bad as we will here. But we warm up way more than the world as a whole. From 3 degrees C to 6 degrees C, depending on emissions. You guys probably don't know C, at least in your daily lives. We use F for Fahrenheit. So this is 5F of warming in the top map versus 10F of warming in the bottom map. Even that doesn't sound that bad. I don't know what your temperature is there today, but you can imagine if it was 10F warmer, you know, it'd be hot, but it wouldn't be like the end of the world hot. But that's not the way to look at this. The way to look at this is where is it 10F warmer on the average? So I'm not going to be able to do this for Sonoma, California, but I have 4 little dots here on the map. This is a map of average high temperatures in the United States in Fahrenheit, and each color on the map is 5 degrees Fahrenheit warmer than the color next to it. And what I'm going to do is take each of these dots and move them 2 colors on the map that is 10 degrees Fahrenheit of warming. And holy shit, mama, this is like Seattle turns into Sacramento. This is like Denver turns into Albuquerque. Illinois turns into Mississippi. So this is a lot of warming. 10F of warming is like moving hundreds and hundreds of miles south. It will change the world. If you think about like the difference between the crops they grow in Illinois versus the crops they grow in Mississippi, those farmers in Illinois or Iowa are going to be completely out of their element if you warmed it up by 10 degrees Fahrenheit. This is not like 10 degrees on the afternoon. This is like 10 degrees on the average. That's a huge change. It's like changing the whole geography of the world, and everybody has to do different stuff for a living and grow different kinds of food. And what is that going to do to crops and health and real estate? And oh my God. So this is a huge deal. Here in the West, the main impact is on water, because evaporative demand, the amount of water that we need, increases dramatically with temperature. When it's hot, we need way more water. So just like heat in minus heat out equals change of heat, water in minus water out equals change of water. And the amount of water in might not change all that much, although there in California, it certainly has changed. But the amount of water out is what really, really gets changed by climate change. We suck massive amounts of more water out of the ground when it's hot, and therefore we run out of water. Drought is not just a lack of rain. Drought is an imbalance between the amount of rain we get and the amount of water that evaporates from our crops and our cities and our livestock and all that stuff. So I'm going to skip this one because it's like depressing and I'm running out of time. Hold on a sec. Oh gosh, here it goes. All right. So here's the big bummer thing about global warming that I kind of hate to tell you, because you guys are young and it's hard to do this to you. And I'm sorry, but this is the way it goes. The warming is basically one way. So what is plotted here? These are time graphs that go out to the year 3000 AD, right? Hardly anything goes out to the year 3000 AD. You never see that kind of thing. In the top, you're seeing the emissions from burning coal, oil, and gas. And there's 4 different kind of what if sci-fi futures. Like, here's a blue curve that shows, like, if we just get right on the stick and cut our emissions to 0 here in the next 50 years, versus what if we wait too long, versus what if we really wait too long with this red line, right? So like emissions are going to grow and grow and grow for the next century, and then they're going to fall after you guys are all dead. Anyway, what happens is that these emissions all go to zero here by the end of the 23rd century, but the CO2 lasts much, much, much longer. So the trouble with this is that after you're done burning coal, oil, and gas, you are stuck with the CO2 in the air. And the total amount of CO2 that you're stuck with is the amount that you've created over all of history, not just the amount you made this year, but the amount that you made this year, plus last year, plus the year before, all the way back to the Industrial Revolution. And so these CO2 curves stay high for hundreds and hundreds and hundreds of years. After you're all done, after the emissions go to zero, the CO2 still stays in the air for thousands of years. It's like we've got our hand on a thermostat and we can crank it hotter, but we can't turn it back down because the thermostat has like a little ratchet in it and it only goes up and it can never go back down. So this is a big bummer. This means that the more we burn, the hotter it gets, and then it doesn't cool off when we're all done. You have to decide before it's too late that you don't want to crank the heat any higher. So the real kind of downside of this is that it can eat your lunch, not just yours, but everybody's lunch. Economically, the damages from unabated global warming can rise much, much faster than the economy can grow. And ultimately, climate change can bring about the end of the economic revolution that's happened since the Industrial Revolution. Instead of having everybody be more wealthy than they used to be, everybody gets poorer and poorer and poorer. And you can just imagine what that does to society and to international relations and to war and conflict and so forth. So we can't go there. We have to stop. We have to figure out a way to avoid those catastrophic damages in the future. And that brings us to the third S, which is solvable. And I want to tell you that this problem is solvable. This problem can be solved. We know what to do. We don't, it's not that we have to invent something new. It's not that we have to figure out something new. We just have to do what needs to be done. And what is that thing? Stop setting carbon on fire. So the thing that we have to do is to stop digging up coal, oil, and gas from under the ground and is setting it on fire to drive the energy of the world. How can we do that? There's fundamentally two ways. One is to use less energy, and the other is to make energy that doesn't involve setting stuff on fire. So this is just an example. It turns out that in the developed world, in the rich world, most of the energy that we use in the world is to support buildings. So we use energy to dig up the ore, to smelt the steel, to transport the materials, to put up the buildings. And then we use energy to heat the buildings and cool the buildings and light the buildings and filter the air in the buildings, all that kind of stuff. So it's almost twice as much energy here in the rich world as we use for transportation. So if you think about your carbon footprint, you're probably thinking about your car. Stop. Think about your house. Think about your school. Think about your office. Those are the places that we actually use about twice as much energy as we do in not just automobiles, but all of transportation. And buildings are getting dramatically more efficient. So here are some projections of U.S. energy use in buildings out to 2030. And back in the dark old days of 2005, we thought the amount of energy we would need to run our buildings was way the heck up here. In 2007, we recalculated. In 2009, 11, 13, you see what's happened here is that over time, we have learned to build better buildings. And that's because architects have finally started taking energy efficiency into account. And we are now using less energy in our buildings than we did 10 years ago or 20 years ago. And just this one change alone will save us, in the US alone, $4.5 trillion in the next decade on energy we had planned to waste in our buildings. And we don't have to do that anymore because we have better, roofs and better windows and better air conditioners and all that kind of better lights. So this isn't because we're freezing in the dark. This is because we're just being smarter about how we use energy. So energy efficiency is by far the easiest, cheapest thing to do to get us out of this big mess. because it saves us money. And the idea is to take the money we save on not wasting energy and invest that in making energy that doesn't involve setting stuff on fire. So simple plan for deep decarbonization: 1, clean up the electricity supply; 2, electrify everything. So the idea here is that we actually know how to make electricity that doesn't involve setting stuff on fire. We have to do that through like solar and wind or whatever. Maybe it's nukes, maybe it's hydro, maybe it's geothermal, all those kinds of electricity that don't involve setting stuff on fire. And then we have to run the whole economy on that electricity, right? So that's really the trick is deep decarbonization by first cleaning up electricity, and then second, electrifying everything. Now, we are super lucky because in the last 10 years, the cost of non-combustion electricity, this yellow line is solar, and the blue line is wind. And the cost of those kinds of energy has fallen by about a factor of 10 in 10 years. I mean, you guys are young, but you can remember 10 years ago. Imagine if other stuff was 10 times cheaper than it was 10 years ago. Like, I don't know, cars. Imagine if cars, instead of costing $30,000, if they only cost $3,000. Imagine if rent went from $1,000 a month to $100 a month. That's what's happened to clean energy. It's fallen in price by a factor of 10 in 10 years. Just astonishing, so that it's now by far the cheapest form of electricity in the United States and increasingly in the world. So it is no longer actually profitable to make electricity with natural gas or coal, because you can do it so much cheaper with wind and solar. Now, of course, the real problem is that wind and solar are not there all the time, right? They're variable energy sources. The real challenge is for getting it from where it's made to where we want it. So like, where is the sun shining all the time? Like Libya, right? Or the Sahara or Southern Arizona. Where is it super windy? Out in the middle of the ocean. But nobody lives in the Sahara. Nobody lives out in the middle of the ocean. So getting it from where it's abundant to where we want it is kind of the big deal. A lot of that is batteries, but even more of it is transmission. And currently, we don't transmit energy more than a few hundred miles. We can't, because it sort of gets stuck in the lines. The lines can only carry the electricity maybe 300 miles before it runs out of oomph. So we need a different kind of transmission. And the way that's done is to use direct current instead of alternating current. And you put just bazillions of volts behind it, and you can transport it almost an infinite distance without running out of juice, which is amazing. So here's a map of the population density of the Earth. And I want you to imagine if we had like infinite energy transmission, we could take solar power from Arizona and keep the lights on in Seattle, right? We could take wind power from Oklahoma and keep the lights on in the East Coast. We could take wind power from offshore and move it into DC and New York City. In Europe, they could get juice from the Sahara up into Germany. They could get juice from the Sahara down into sub-Saharan Africa, where there's millions and millions of people without electricity. Thinking even bigger, we could use wind power off of Scotland to keep the lights on in Beijing. We could use solar power from Saudi Arabia to keep the lights on in India, and so forth. So once you have transmission, you can put clean electricity where it's very, very abundant and get it to where you need it when you need it. So all of this is going to cost some serious amount of money. Conversion to 100% non-combustion energy is going to cost about 1% of the total economy of the world. Now, you probably don't know or care what the whole global economy is worth, but I'll just tell you it's about $100 trillion a year. That is, if you add up all of the stuff that people buy in a year, it's about $100 trillion. And 1% of that is $1 trillion a year. Now, that's a lot of money, even, in Washington, D.C. But if you just think a little more broadly, that's about what it costs to retrofit all the world's cities with indoor plumbing 100 years ago. Imagine what it would cost if you tried to do this today with union plumbers to dig up every street in Washington and New York and LA and lay sewer lines, to knock out tenement walls 20 stories high and put in hot and cold running water, to knock out interior walls in every apartment on Earth and put in toilets and sinks and showers. Believe it or not, our ancestors actually did that. That's an astonishing infrastructure plan. And it was so worth it, because not only do they have toilets now, we have toilets now, and we don't have to poop in the street, but imagine what it did for plumbers. Imagine what it did for plumbing suppliers. Imagine what it did for the grocery store down the street from a plumber, or the children of that plumber who could then use that money and go to college. So money is never gone when you spend it. In a capitalist economy, it goes round and round and round. It gets spent over and over by the people who make that money. These are my grandparents. That's Max and that's Francis. And it was their generation 100 years ago that actually did that gigantic project of digging up all the streets and putting in, I mean, it wasn't them personally, right? But it was like that generation that replumbed the cities of the world at a cost of 1% of the world's economy. And now we have toilets. Yay. But they weren't done then. When they were done with indoor plumbing, they built subways. They electrified the world. They put separate little copper wires to every farm in Nebraska, so that everybody could have lights and TVs. They fought World War II and defeated the Nazis. I mean, they were just like this amazing generation that did all this awesome stuff. And they didn't go broke doing that stuff. They actually made the world better, and they created all of the jobs and prosperity in their entire generation, which was really a powerful, amazing generation that did cool stuff. These are my parents. That's Margie and that's Bob back in the 1950s. And their generation did gigantic things too. They built the interstate highway system. They fought the Cold War. They landed people on the moon. These were gigantic projects that cost more than 1% of every dollar on Earth. And those projects did not make my parents' generation go broke. They produced all of the jobs and prosperity in the 1960s that lifted my parents' generation out of poverty. This is me and my wife back when I had hair, back in the 1990s. Our generation did awesome stuff too. We invented PCs, not me personally, but we built billions and billions of PCs, and we put them on every desk in every office on Earth every 3 years for my entire adult life. Then when we were done with that, we built the internet. And then we replaced billions and billions of landlines with cell phones. And these were all gigantic, huge projects that if you tried to do it like from scratch today, oh my God, that would be punishingly expensive. But guess what? We didn't go broke doing those things. That's what produced all the jobs in my entire adult life, and all the prosperity in my entire adult life was actually rebuilding the communications infrastructure of the planet. These are my kids. That's Matt and that's Nate. And they get to do it again. Their generation gets to replace aging, creaky infrastructure that is ruining the world by setting shit on fire with energy that will produce lights and heat and manufacturing and transportation and all the good stuff for your generation without setting stuff on fire, without destroying the world. And this will, yes, cost 1% of the world's economy. And yes, it will produce all of the jobs and prosperity in your generation, just like all those other giant transformations did for the last several generations. This is not new. We have always done this since the Middle Ages. Humans have invented new stuff that was more expensive than the old stuff, but was better than the old stuff. And we've done it over and over and over again. That's what makes us not medieval, right? That's what makes us modern people. You get to think about your future. You can think, our well-being is based on stuff we extract out of the ground. There's value in a lump of coal. You dug that coal out of the ground and you sold it for a profit, right on. Then somebody bought that coal, they set it on fire, and they sold the energy for a profit to somebody who bought the energy and used that energy to make products and services that they sold for a profit. And it goes round and round and round. And before you know it, you got $100 trillion a year global economy. And maybe that is the way that the world works. But oh my God, I hope not. Because that story has a sad ending. That story ends when either the coal runs out or we decide to stop burning it. And what? The whole thing just collapses and our descendants shiver in the dark, only there's like 10 billion of them and now they're hungry too? What the heck? That's no good. That's a terrible story. I hate this story. I like this story better. We create our world. We create our own well-being through creativity and ingenuity and hard work. It comes not from stuff that we dig out of the ground, but from the sweat of our brows and the spark in our souls. and we're not going to run out of that, and neither are you, and your future can be bright if you want it to be, and you don't have to be doomed. That's it. I'm done. And now I'm going to stop sharing, and we can go to Q&A.
Stay green. Stay green. Stay green. Let's go green. Stay green. Let's go green. Stay green.